This lesson is about the absolute value as a function. In the previous lesson, we saw absolute value inequalities and equations using the distance definition of absolute value of x. Recall that absolute value of x is the distance between x and 0. And such quantity or measure can't be negative. Distance, or absolute value of x, can be either 0 or a positive number. Here we have an algebraic definition for absolute value of x. What you're seeing here is called a piecewise function. We have a function that is defined as two separate pieces, x and negative x. Each piece is on a specific interval. Here we have x greater or equal than 0. Here we have x less than 0. So what this is saying is that absolute value of x is equal to whatever x is. If x is positive or 0, and if x is negative, then absolute value of x becomes the negative of x. Let me try to explain this piecewise definition because some students are confused by this negative. They think to themselves, absolute value can give you a negative, so why should there be a negative? Let's look at the cases. For x positive, say x equal to 5, we're going to get absolute value of 5 equal to 5. Keep in mind that this is absolute value of x. I have chosen x to be 5, so absolute value of x is absolute value of 5, and that is equal to 5. Well, the same exact thing as x. So if x is positive, absolute value of x gives you x back. Well, what about 0? For x equal to 0, we get absolute value of x, which is absolute value of 0. That is 0, and that gives you still x back because the distance between 0 and 0 is 0. That is why in this piecewise definition, absolute value of x is the same as x when x is positive or 0. What about x negative? Say we take x equal to negative 5. Then absolute value of x, which is absolute value of negative 5, is equal to 5 because the distance between negative 5 and 0 is 5. We did not get x back. X is negative 5. But the output is the opposite of it. We really have the negative of negative 5 back, which is the negative of x. If I take a negative number, absolute value of that negative number is the negative of the negative number to guarantee that we end up with a positive value. As you can see, this graph consists of two pieces. We have line y equal to x, and that's over x greater or equal than 0. So over this interval, we have y equal to x, and over this interval, which is x less than 0, we have y equal to negative x. The line with a slope of negative 1 going through 0, 0. This line is only drawn on the interval x less than 0. Keeping this definition in mind, we can rewrite absolute value expressions as piecewise functions, and that will come handy in calculus. So let's break this down, absolute value of x minus 5 can be broken down into two pieces. You can get x minus 5, absolute value of something is equal to that thing, to that number. If that expression or that number, in this case x minus 5, is greater or equal than 0. On the other hand, absolute value of something is the negative of that thing, in this case the negative of x minus 5. And this happens if inside of the absolute value x minus 5 is less than 0. Notice that we are using the same definition. Instead of x, we have x minus 5. So just replace x with x minus 5 anytime you see a different argument instead of x. Let's indicate what the intervals are. I can write this as the line x minus 5 if x is greater or equal than 5. What I have simply done is I've moved this negative 5 over. I added 5 to both sides, which tells you that if x is 5 or more than 5, we get the line x minus 5. And we get negative x plus 5. I have distributed the negative in. If x is less than 5. And again, for the second inequality, I've added a 5 to both sides of the inequality. This is our piecewise definition. Let's graph this piecewise function. Here is 5, and this 5 separates the x-axis into two intervals. Everything before 5 and every number after 5. For x equal to 5 or more, we have this piece. You're going to draw this piece over this interval. Let's look at this interval. This interval includes 5, 6, 7, and so on. We can start by choosing 5. If you put 5 into the green piece, 5 minus 5 is 0. I am using a solid point because 5 itself is included. To draw this full line, I just need another point. It should be in the part where x's are more than 5. Say we choose 6. Then put 6 into the green piece. 6 minus 5 is 1. So 6, 1, right about there. Connect the 2 points and you have y equal to x minus 5. To draw the second piece, I have to choose numbers over this interval. This interval has a boundary point of 5. 5 is not included in the interval, but it's a boundary point. You want to know where graph begins. So you're gonna start by picking the boundary point itself, 5. If I put 5 for x, I get negative 5 plus 5, and that results in 0. So 5, 0 is right there, but as you see, the point is not solid. It's a hole because 5 itself is not included like before. To draw the full line, I need another point over this interval, x less than 5. I can choose, say, 4, 3, 2, or 0. Let's plug 4 into x. You get negative 4 plus 5. That is equal to 1. So at 4, we have 1. connect the 2 points. Remember that the first point is just a hole. There you have the full graph of absolute value of x minus 5. The other piece that I've just drawn is y equal to negative x plus 5. This full graph is the graph of absolute value of x minus 5. You could have drawn this graph by identifying the shift. It's x minus 5. That means the graph of absolute value of x is going to move to the right by 5 units right there. So same graph translated by 5 units will give you the graph that you see on the screen. You might say I can just use transformations, just move the V-shaped graph according to shifts if you know transformation rules. But let's look at the next example, which is a little different. This is a fraction involving absolute value. Since it's a fraction, it could be undefined. The domain of this function is not all reals. Notice that in the denominator we have x plus 1. Let's write out the domain of this function. Domain is all x such that the denominator x plus 1 can't equal 0, or x is such that x can't equal negative 1. Negative 1 makes this function undefined. You get 0 in the denominator. Acknowledge the domain. The second thing you want to do is to break up the absolute value part. Begin by rewriting absolute value of x plus 1 in piecewise form. There are 2 pieces. Absolute value of x plus 1 is equal to x plus 1 if x plus 1 is greater or equal than 0. Okay. If this expression is 0 or positive, you just get that expression back. Again, just like absolute value of 5 equal to 5. And we get negative of x plus 1 if the expression inside the absolute value of x plus 1 is negative. Remember, if this is negative, to guarantee that we end up with a positive, you have to multiply what's inside the absolute value with an extra negative. Negative times a negative is positive. Let me just rewrite these intervals. The first one is x greater or equal than negative 1. I'm subtracting 1 from both sides. And the second one is x less than negative 1. Let's keep this piecewise definition in mind. Now let's go back to our function. What we are going to do is we are going to take the definition for absolute value of x plus 1 and divide these by x plus 1. So absolute value of x plus 1 was either x plus 1 if x was greater than or equal to negative 1, or negative of x plus 1 if x is less than 1, but we are dividing by this x plus 1, so take each piece and divide by x plus 1. Since x can't be negative 1, we must remove the inclusion of -1 from our domain. We're just going to erase that. There we go. And all you gotta do is simplify each of these. X plus 1 over itself is equal to 1. For the second piece, negative of x plus 1 over x plus 1 is -1. These simply cancel out. So our function is either 1 or -1. I'm missing a negative here. Let's draw the graph of this function. Here is -1. What this is saying is that if x is greater than -1, that would be over this interval. Then the value of y is always going to be 1. So over that interval, we are going to draw the horizontal line y equal to 1. Notice that this is a hole because -1 is not included in the domain. And when x is less than -1 over this interval, we get y equal to -1, the horizontal line at -1. So this whole thing is this function. It is a discontinuous function. It has a jump. If you're drawing this graph, let's say we draw just this piece, we have to remove our pen, then draw this piece. This has what we call a jump discontinuity. Let's look at the third example. This requires a little bit of work. Just like the last problem, we're going to begin by breaking down the absolute value part. We want to write absolute value of x squared plus x minus 6 in piecewise form. What you need to do is just like the original definition, say that this is equal to what is already inside the absolute value, x squared plus x minus 6, if x squared plus x minus 6 is greater or equal than 0, and it is the negative of x squared plus x minus 6 if this quadratic is less than 0. Notice that here we have a inequality that is non-linear. Non-linear inequalities must be solved using sign analysis. I also must mention that the domain of this function excludes -3. Here x can't equal to -3 because -3 makes the denominator 0. Division by 0 is not allowed. Now, to identify our intervals, we must solve these inequalities. To solve the inequalities, we have x squared plus x minus 6. Factor it out. This factors to x plus 3 times x minus 2. You want to know when this expression is positive and when it is negative. Draw the number line and locate the zeros of these factors on the number line, because it is at the zeros that the expression can possibly change sign. For this factor, the 0 is -3. For this factor, the 0 is 2. Our factors are x plus 3, x minus 2. You can begin by choosing test points. Let's say I test any number less than 3. Let's say we test -4. You can test -5, -10, -1,000,000. As long as it is less than -3, we are good. -4 plus 3 is a negative number. -4 minus 2 is a negative number. And double negative is going to give you a positive. From -3 to 2, we take a test point, let's say 0. 0 plus 3 is positive. 0 minus 2 is negative. That's negative. We have positive times negative. This expression is negative. Over the interval 2 to infinity, we're going to test any number larger than 2. Let's say we test 3. You can test 4 or anything again more than 2. 3 plus 3 is a positive number. Here 3 minus 2, that's a positive number as well. We have positive times positive. That means the quadratic expression is positive over the interval 2 to infinity. Here is the result of our sign analysis from the previous page. It's going to help us rewrite our absolute value part. Two things will happen. We're going to get x squared plus x minus 6, or we're going to get the negative of it. I'm going to write this down in factored form. X squared plus x minus 6 is x plus 3 times x minus 2. And this is happening again where the expression is non-negative. That happens here and here. So it's from negative infinity to -3. I can write it as x less than or equal to -3, or x greater or equal than 2, which is this interval. We are going to get the negative of, for the second piece, the negative in factored form, x plus 3 times x minus 2. This happens if x is between -3 and 2. This is the double inequality, means between -3 and 2. Alright, so this is the piecewise form of the absolute value part of our function. Now, we are going to take these expressions and divide them by x plus 3. Alright, this is the piecewise form of our absolute value expression. Absolute value of x squared plus x minus 6. Our function here is this absolute value divided by x plus 3. So what I'm going to do is we'll divide the pieces by x plus 3. Now, since we have a fraction, the denominator again can't be 0. Remember, we've already said that the domain excludes -3. Therefore, from this inequality, we must remove -3. And there we have the piecewise definition of our function. We can simplify this further. We can rewrite our function in a simpler form as x minus 2 on the interval x less than -3 or x greater or equal than 2. And for the second piece, we can also cancel the x plus 3's. To rewrite what we have, I'm going to distribute the negative inside of x minus 2. That becomes negative x plus 2. And this is happening over the interval x between negative 3 and 2. This is our function, f of x. It's a piecewise function. We can graph it. To graph a function, we have to be mindful of the intervals. Things change at negative 3 and 2. Let's begin by drawing the first piece. This piece is going to be drawn over 2 separate intervals. Over this interval, x less than negative 3, I'm going to begin by choosing the boundary point or the end point. We start with negative 3. If you put negative 3 into x, you get negative 3 minus 2. That would be negative 5. So at negative 3, we have negative 5. That's one of the locations that determines our graph. Notice that since negative 3 itself is not included, we draw a hole. For x less than negative 3, I need to choose a number less than negative 3. I can choose negative 4 to pick another point on that graph. So say we choose negative 4, plug it into the piece. Negative 4 minus 2 is negative 6. Add negative 4, negative 6 is that point. Connect the two to draw the line x minus 2 over this interval. Now, this line is going to be also drawn on the interval x greater or equal than 2. That would be this interval. We're going to start by plugging 2. This interval starts at 2. Put 2 there, you get 2 minus 2, which is 0. I have to use a solid point because 2 itself is included. To choose a second point, we can take a number such as 3. Remember, the interval is x greater than or equal to 2, so we have to pick points over this interval. Put 3 into the green piece. 3 minus 2 is equal to 1. So 3, 1 is going to be a point on the green graph. Connect the 2 points and you have the other portion of this line. For the second piece, which is negative x plus 2, we're going to choose points that are in this interval. We always begin by choosing the boundary points because we need to know where the line starts. I'm going to begin by plugging negative 3 into our piece. But here we get negative of negative 3 plus 2. That is 3 plus 2, which is equal to 5. So at negative 3, the outcome is 5. And of course, we are going to draw a hollow point because negative 3 is not included itself. I can choose the right end point of this interval, 2, to see where the line ends. Put 2 inside the line, you get negative 2 plus 2, that's equal to 0. So when x is 2, we get y equal to 0. 2, 0 is a hole according to that line. This piece starts here and ends there. this hole is already filled in by the green line. X equal to 2 is in fact in the domain, so it's not as if there is a hole there. The hole was filled in by the green line. Again, this is a graph that is not continuous. There is a point of discontinuity at x equal to -3. We have a jump.